Many thanks for coming. Today we're going to have three sets of presentations just demonstrating researchers' work in CSIS/Lero and their most impactful research. First up will be Conor Ryan. He's going to talk for about 15 minutes on flash drives and essentially prolonging their operational lifetime. Then I'm going to come in with something called clone detection at scale. And finally, we're going to hand over to Christiana, who's going to talk about designing technology for chronic self-care for people with chronic illnesses, their self-care. It's going to be about 15 minutes of a presentation each, followed by one or two questions from me, if you'd like. And maybe if there's some spare time at the end, we might have a cumulative conversation. Okay, so without further ado, over to Conor.
Thanks, Jeff. I'm going to take a strip, so which I found is useful to take at the start of any talk. Okay, folks. So my name's Conor Ryan. I'm from the Computer Science Department, and I'm going to talk about flash memory. So flash memory is the ubiquitous memory today. Okay, it's everywhere. It's in USB sticks. It's in SSDs that you find in the computers, and some data centers. Flash memory is fantastic. It's super cheap. It's very fast, it doesn't use much power, it doesn't generate very much heat, but it does have some problems. So just to see what the problem is, so let's work through the actual flow of it. So you take a photograph, I'm going to pass on to my flash device. Okay. And what the device does is it breaks it up into what are called blocks. And these are going to be what's going to be written onto the actual flash device. So when we want to read back that picture, read back all of the blocks, reassemble them, and then we have our image. Now, the problem with flash is that it has errors. Okay, so right from the very start, every time we read back a block, there's a couple of errors in it. And it's such a problem that all flash comes with what is called ECC, it's error correcting codes. And as you read back in the block, it tries to figure out, well, what did the person actually mean to write in here in the first place? Fixes the errors, hands you back a clean block, and you get your picture back. Now, the problem is, as the flash gets older, it has more errors. So the more you use it, the more errors you have. And importantly, the more you just leave it alone. Okay, unpowered, in a drawer somewhere with your beloved photographs on it, it will have more errors as well. And eventually, you can get to a situation like this, where the ECC engine will take the block and say, there are so many errors in this, I can't decode it, I don't know what the person wrote. You're on your own. So then your beloved picture goes like this. Okay, that's with 10% degradation in the blocks. Now we're up to 30%, and here 50%. Because the total degradation of your photograph, and once it's gone, it's gone. So what I'm going to talk about today is how we tackle this problem of flash memory using machine learning, and it was quite successful. Okay, so we were able to spin out a company that was eventually acquired in 2018. So I like to make a distinction between machine learning and artificial intelligence. Now, a lot of people just treat them as though they're the same thing. So machine learning is the ability of computers to learn for themselves. Okay, so where we don't already know how to solve the problem, we get the computer to learn how to do it. This idea has been on for a long time. So Arthur Simon from 1955 coined this term. Well, the first early wins for artificial intelligence was Deep Blue, the chess player back in the 90s. And it was very good, okay? It was able to beat a chess grandmaster. But that's all it could do. Okay, so the whole thing's a total cheat. So we knew how to play chess very well, programmed the machine how to do it, but that's all it could do. Later on, about 20 years later, Google DeepMind came along and it learned how to play Go, and it beat a grandmaster. Now, it's an awful lot more impressive because it didn't know anything about the game at the start. It just learned how to do this by playing it by itself. Now, all machine learning works roughly the same. You've got a bunch of claim data, passing some sort of learning system, and it produces what I call an executable model. So let's just think about that as a computer program. So it learns how to write that program itself. And here's what the data looks like. Okay, so we have our attributes across the top there. So for example, for this audience, it could be what's the gender of the person, what's their age, what's their educational background. And we have observations, which would be each person who's here. And we have a label. Okay, so for example, for something like this, it could be what do people think of Cristiano's talk? Okay, people in green like to talk, people in red didn't like it so much. Okay, if it's say for Jim,
Not a red.
here's what Jim's might look like. So, similar data, slightly different distribution. Now, where the magic happens is when we have data that we haven't seen before, that's in the same distribution, and we ask the machine learning system, okay, the model produced, what do you predict this person is going to do? All right, so we have our input data that we haven't seen before, put it into the executable model, and it makes its prediction. So here's the problem with flash memory. Right, down at the lowest level, okay, inside the blocks, you've got these things called floating gates. Okay, and there's one of these for each bit of storage. Okay, so these are tiny. And when we want to write something to it, we charge it up, and a whole bunch of electrons stick onto that floating gate. And when we turn it off, they stay there. When we want to erase it, we send another voltage through it, which is even higher, and we knock them all off. Here's the erase state. Now, the little black dots there represent electrons. Okay, so even when it's erased, there's still a couple of things stuck to it. Here's what it looks like when it's programmed. Okay, so we have more of them there, so we can tell the difference between that state and the earlier state. We job how you're looking at the voltage threshold. Okay, if the voltage is above a certain level, it means one thing. If it's below, it means something else. Here's the problem. The more we use it, the more the electrons just get stuck to it. So even when we try to raise it, they'll stay there. Eventually we get the situation of this, where there's so many stuck to it, we just can't delete anymore. So this is the problem we have. Okay, if we go too high with it, if we go too strong.
I'm so sorry.
okay.
They went late.
So if we go too aggressive with it, if we're too strong, we'll damage it and it'll die faster than we need it to. If we're too weak, okay, if it's too soft, then we'll lose its contents very fast. And it's called a retention problem. There's with endurance versus retention. Now what we want is something here in the middle, what we call the Goldilocks zone, where it's just right. It's not too soft, not too hard, it's just perfect. So it means it'll retain everything that's written to it for as long as possible, but we won't damage it. The difficulty here is this area gets smaller and smaller as the flash gets older. Because then we just have this tiny little area and it becomes harder to write into that flash in such a way that we're not damaging it and that we have a proper retention. Now setting these values is very difficult because we have all these controls to say how the write's going to work. And there's multiple controls, what we call registers, that'll dictate how strong they're going to be. What we want to discover using machine learning is what are the optimal control parameters. And this could be maybe 200 different parameters that all interact with each other in some way. And what we came up with was having variable ones. This is dynamic, so they change during the lifetime of the flash. So we have one set early on in life when it's very fresh, another set then later on. But typically when people think of artificial intelligence and AI, they do something like this. But the one super smart agent, like a neural network or like GPT, that knows a little bit about everything. We use something very different. Okay, because the problem with something like GPT is that if it doesn't know about the topic already, it's going to do very badly. We want to be able to learn about the specific flash and figure out how we best set it up. So in evolutionary algorithms, we have a population of what we call individuals. And each of these basically represent a potential solution. Okay, so for example, it could be a parameter set that make the device last as long as possible. There's some way of testing each of these. Okay, so here's the more green we see, the better the thing did. Because that is, the longer it lasted, or more properly, the fewer errors it had at the end of life. And these populations can be big. We could have thousands of them, or hundreds of thousands, or even millions of them. Now, each of them can't learn anything by itself. Okay, it just represents a possible solution. So here's how the algorithm works. Okay, we randomly create a whole bunch of individuals with our potential solutions. And we have to test them in some way, okay, to see how many errors they have left after the end of life. And we probabilistically select them. Okay, so the more adapted they are, the more green they have, the more likely we are to choose them for the next stage. Then we'll recombine them. So we take them two at a time, take some information from one from the other, and it gives us our children. Great, then we introduce some variation by mutating a couple, just by making small random changes. And that's our next generation. So we've all the offspring, we have the mutants separated there, throw a couple of the parents just for good measure, and then we iterate through that whole thing again. So we test everybody again, and ideally one of them will appear who correctly solves the problem. Okay, so it's a set of parameters that make us last as long as we need. But this is an iterative process. So okay, we keep going around in circles. Now, that's an old technology. Okay, so we didn't invent that. What we invented was the idea of having multiple parameter sets and a fast way of testing them. And here's the thing that did the testing, okay, which imagines what we call the flash tester. We put a piece of flash into that, okay, just this is basically just a silicon chip. There's what's called a daughter board that lets us interact with that piece of silicon. And even an embedded computer where we could have a program running that would do various tests for us. Okay, it was a crucial piece of the technology. And it was just so we could know which way out the actual chip went. Now, when we started doing this, we realized that there was a real hunger for a device like this. Because this is early days of Flash, and people didn't really know how to test it. So we had a really cheap tester, so we were able to test Flash for people, and also then started selling these testers to people. So here's an early prototype of it, where it's got kind of a casing, and we decided we'd try and sell these as a company. One of our key tests at this point was the CAT test. You can see in the background there, I've got a couple of testers on the desk. And the CAT test was, if the testers were generating so much heat that the cat wanted to sleep in them, it was probably generating too much heat. There was a first product, which we called the grey box. The Tipex still playing a big part in the whole system. Now, you probably think this is just a very ugly looking grey box, and it was. Okay, but it was the only cheap ugly grey box at the time that could test Flash. So we got a lot of business where we tested all the people's Flash and saw what the problems were. Because of that, we then filed a bunch of patents on how these people should have solved their problem in the first place. Instead of incorporation in about 2013, we got a bunch of investment, some from within Ireland, others from outside. Then we had to choose the name of the company. Now, initially, we were going to have Flash as part of the name because of the technology we were looking at. But we were told, don't use Flash as part of your name because nobody will be using Flash in 10 years from now. Back in 2013, and it's still all over the world. So we got rid of these ones. So NAND was just a type of Flash we were using. Other ones with Flash were removed as well. We were going to call the company Mendurance. Okay, so memory endurance. Then somebody discovered this product, Mendurance. Now, I'm not familiar with the product, but I just
Thanks for clearing that up.
just in case, okay? With non-volatile memory endurance was the name of the company. So remember, okay, I need about 4.
Yeah, okay.
We need to set optimal parameters. Ideally, we're going to have multiple ones. So we want to use machine learning to try and figure out what they should be. Now, machine learning is going to use a whole bunch of data because it needs a lot of data to learn from. And this is a real problem for Flash. Okay, so we have to cycle these things in EO time. So it takes 10 days to run a test on Flash because we're actually physically destroying the piece of Flash. You have to enumerate every possible combination. That's 7 quintillion years it would take. Okay, that's 7 followed by 16 zeros. Okay, more time than we realistically had access to. And it's just destructive testing. So every piece of Flash we test gets destroyed. So here's how we got over this problem. We generated a small amount of data by testing them in actual hardware, okay, and destroying the Flash as we did it. We then built a whole bunch of machine learning models to predict from that small data set what an unseen data set would do. We searched through all those models using evolutionary algorithms, and we did this at scale. Okay, so this with billions of individuals. But they found the ones that looked like they were going to be good. Tested them in hardware again, and this is important because every time you test it, you get a slightly different answer. Okay, so this is a real problem for Flash. The ones that looked like they could be good, and even the ones that looked like they could be bad, but then fed back into the models. We rebuilt the models to have something that's going to be more accurate. And this is the key thing about machine learning. It's not enough to have data. It's important to have the right kind of data. Because there's so much data there, it'll take a long time to search it. So it's almost solved the problem. But surrogate-based testing is what we call this. That has got us up to 350 years. We're still destroying the Flash. But then, through a lot of clever electronics, we were able to do all this in parallel. So we got the whole thing down to 90 days. And that's why it was success. So we started to scale up. We got a bunch of employees, had a bunch of large-scale customers. In 2015, we had a prototype SSD. This is a big device, it's about that size. Wouldn't fit into a computer, but it did prove that the thing worked. There's NVIDIA endurance as part of this. In the following year, we had our first product. This is an actual SSD that could fit into somebody's computer, sold by a company called Mobivale. The year after that, this computing device here, made by NVXL, also using the same technology from us and from Altera. Then there was an acquisition offer came in 2017. So I was going to finish with what actually happens in an acquisition. Because oftentimes it seems like, somebody comes along, offers to buy a company, and everybody makes a fortune, it's all great. Not quite what happened with us, okay? And this is kind of typical of what happens to people. Company came along and said, we love your company, we love you, we think you're fantastic, we'd like to buy it. One of their competitors came along and said, actually, we love you even more than they do. We'd be way better to you, so why don't you come join us? So we're delighted. We think we're going to make a fortune. Panic ensues, we talk to everybody we can. Lawyers are called in to try and negotiate with these people. They get to look at our technology in detail. First company comes back and says, you know what, actually, now that we've looked at it, we hate you. Your product is crap, so are you, but we're still prepared to buy it. Okay, they basically wanted to lowball us. Second company came along, said the only thing we hate more than company one is you. But we're still prepared to buy you because we hate them so much. In the end, you them bought us. It was a third party. There's an NDA in place that I can't see who actually bought that. But what I can tell you is they bought a whole bunch of other companies doing something similar, and they're still doing it. So even though Flash is all over the world and used by everybody, there's still problems with it, and people are still trying to fix it. So next time, take a picture. This is Kitty Fluff. Remember, Flash is going to destroy it. It's not a question of if, it's when it's going to be forgotten. So thank you.
So any particular questions on that? Any specific questions on that? Yeah, Farmer.
Thank you so much for. I knew about the CSIS product architecture. This is first time on.
Okay.
And I'm missing all these details. So the dynamic parameters or the optimal parameters which you figure out, how many were they? Do you have any idea?
Okay, so it was dynamic parameter sets. Okay, so at the simplest level, it would be a set of 200 parameters, and we changed that multiple times during the lifetime of Flash. Now, in the early days, with the example I get there, it might have been 2 or 3 times, but the later ones, there was more registers, so there's up to 2,000, and we would change them very fast. So we would change them maybe 64 times during the lifetime of Flash. So we'd observe how's Flash degrading, and we'd have to try and preemptively change parameters to make sure that the next time we write something, it's not going to be forgotten.
Because I wonder, did it have any impact on your surrogate model as well?
It made it a whole lot more complicated. Yeah, because the surrogate models they actually ran on Amazon EC2, and because of our timeline, we had to get them running in 4 days. So they ran across, I think, 2,048 processors, and you had to pay for access to the Amazon, and each run cost us €6,000, and we were a tiny company. So this was an astronomical amount of money for us. And so if anything went wrong, it was a disaster. But we were able to test the whole thing in scale, and within 4 days, have another set then that would be tested in hardware. We had kind of a 2-week cadence for each set. Thank you.
I guess we'll just leave it at that for this, and if there's a few minutes at the end, we can return to more general questions. So, yeah, thanks, Conor, for a great talk. I think there's a curse known as "May you speak after Conor Ryan," and you're going to see why now, because this isn't going to be anything as cool as that. And there's another curse: "May you speak before Cristiano Ronaldo." Cristiano started. Yeah. Okay, so I'm going to talk about something called clone detection at scale. Just to decode that a bit, it's sort of like plagiarism. The idea that, Tom's sitting there beside Mary in this, baby infant's class, and he sees 3 + 5 really is 8, so he puts 8 down on his own. So it's this idea of claiming someone else's work as your own without acknowledgement or without their express permission. And it turns out that there's a long history of programmers doing that too. So the idea is that programmers trying to implement some functionality, and they go, that's got to be out there somewhere already. So what they do is they look for it on the web, and they find a bit of code maybe in some open source system, and they say, yeah, that'll do. I'll need to change it a little bit maybe, but I'll use that for my needs. So they cut and paste it. And they may even change it very slightly, but more or less it's an identical clone of what was here. Okay? What are the problems with that? Well, if you cut it into a proprietary system and paste it into a proprietary system, maybe there's a license in that open source system that says, yeah, you're free to use this, but don't use it in proprietary software systems. So all of a sudden they're in license violation. Another alternative is that maybe there's a small error in this, a small vulnerability. So essentially, Mary's answer was 9 instead of 8, and you've copied 9 in here instead of 8. So you've got a problem now in your code. Someone 2 years from now might find the problem here and go, oh, we should fix that. But of course, the team who cut and pasted it in have long gone, long forgotten that they ever cut and paste this in. So you've now got a vulnerability that you've imported into your system that you don't know about. So they're the 2 scenarios that we want to address here. And I suppose what we want to do is we want to find these clones. And that's made a bit more difficult by the fact that the moment you move them into this new context, you might change them slightly for that new context. And certainly as the project that you copy them into evolves over time, it's likely that these will change over time. So they become less and less exact clones of the original clone. So a Chinese multinational came to us and they said we would really like to detect inexact clones that have changed a bit, from open source software that we may have copied into our system in the bad old days, so that we don't get caught for license compliance purposes, and so that we were aware of vulnerabilities that have since been identified in the open source projects. So we had 3 research questions as part of this collaboration. I'm just going to talk about the first one first. So how can we optimize clone detection at scale, inexact clone detection at scale? And what I mean by at scale, this company have over 1 billion lines of code, and they want to compare it to open source, which has many billions of lines of code. So that's really at scale. So just to give you a potted history of the clone detection world, approaches for finding exact clones, it's already more or less sorted. We know how to do that accurately and quite at scale. So we wanted to concentrate on the inexact clones. There are some state-of-the-art AI approaches that have arisen showing promise for more inexact clone matching, finding those clones, those inexact clones. But they typically, what they do is they say, okay, I take this piece of code, convert to this piece of code, this piece of code, this piece of code, this piece of code, this piece of code. Then I take this piece of code, I convert to this piece of code, this piece of code, this piece of code. So there's an awful lot of comparisons, n-squared comparisons happening here. So that makes them quite inefficient. And there's an approach called Oreo, which uses a lot of heuristics to try and get around that, but it still takes it 1 day, 21 hours to work through a standard benchmark in the field, which is 250 million lines of code, below our requirements, really. So what we decided to do was to try and get away from this pairwise comparison, and we at the time, which was like 21, 22, we started hearing about large language models, LLMs, and BERT was one that was happening at the time, and getting good results in English. So the idea of BERT is, it stands for bidirectional. So say we're encoding the 8, we look in front of it and behind it to give us context for it. And we encode it using some sort of model that's trained on generic training tasks. So that's the encoding, to a representation, a vector representation using this deep learning transformation model. So that's where BERT comes from. But once you have that generic model, then you can specialize it for subsequent more specific tasks by specific fine-tuning training, okay? So we said we were going to try and do that. So here's what we came up with. We said, sorry, one thing I should have mentioned was that this was so successful that a derivative of CodeBERT was created, which instead of encoding English, encoded code. So that was much more interest to us. So we were going to use CodeBERT. And the idea was that we had the generic model created for us. We wanted to fine-tune it with clone pairs and non-clone pairs towards creating those vector representations. And the idea was, if these 2 pieces of code were clones, then they'd end up close together in that vector space. If these 2 were non-clones, they'd end up far apart in that vector space. So that was what we were trying to do. So then when we had that, we could use a nearest neighbor in that vector space to identify things that were more likely or less likely to be clones. So once we had the fine-tuned model, we could take a sight unseen to create vectors for the pieces of code. And then I've reduced this to 3 dimensions from 768 just for visualization purposes. Yeah. But the idea is that if 2 pieces of code are quite near, they're more likely clones. If 2 pieces of code are far apart, then they're more likely non-clones. So that allows us to give a ranked list of clones back. And we can use a nearest neighbor algorithm, which means that we don't do this combinatorial comparisons. We do much less comparisons. An interesting thing here, if you're in pure academia, you start to go, a technique like this, we want to report on recall, we want high recall and high precision. So recall is that you identify all the clones, you don't miss any, and precision is that you have few false positives. You know, together they're a nice sort of accuracy measure. But that wasn't this company's interest at all. They said, no, we want to recall as many as possible. We want to find all the clones. And we don't really care about precision. You know, it's just a developer going through these pieces of code saying, yes, that's a true positive. No, that's a false positive. So they said, we're willing to go down to precision of 0.2, that 4 in every 5 will be false positives. We just want to find them all. Wow. So that was very much an applied lesson for us, that, you know, these standard academic measures weren't really what companies were necessarily interested in. So I just talked about that there. Should have delayed myself. So this is our approach. We tried it on 13 million lines of their code with 300 million lines of open source code. And what we got? Well, we got 133 candidates out of 664. That's 20%, a precision of 0.2. So that's what we were measuring. And we found 101 inexact type clones. Now, their existing solution, which was CC Finder X, found 16 of those. So that was a bit of a win for the company. We were very happy with that. Iteration 2 was quite simple. We decided to do some pre-processing. So what I mean by pre-processing is that we did some work on the code coming in just here and just here. One of the things I would do if I'm cutting and pasting code is I'd take the code from one place and it would have a certain layout because that would be the conventions of their project. When I cut it into a new project, I'd change the layout so that it was consistent with the new project. So really what you're saying there is white space is a confusing factor. The white space would be different between the originator and the clone. So we just removed white space, any tabs or anything like that, we just made one white space between them. When we did that, we got a huge improvement. So we found 192 clones, whereas their previous solution found 26. So that was kind of nice. And again, the company were kind of happy with that. Of course, that was then. As the project went on, more and more LLMs were being released on a monthly basis, really. So we decided, let's look around to see if there are better models than BERT now. So we looked at 3 reviews of LLMs in software engineering and our own work in code detection, the papers that have come out since, and we found 76 different LLMs. We had some criteria. You had to be able to do the LLM work locally. They didn't want to export their code up to the cloud to have it analyzed for obvious reasons. It had to have some source code training task applied to it to tune it. And of course, it had to create the vector representation. They were the 3 criteria. When we applied those 3 criteria, we got down to 12 LLMs. We tried to integrate them into our original tool, and we were successful with 9 of them. 2 of them didn't handle C or C++, so we couldn't take those, and 1 we just couldn't work it. It just didn't work for us. So we were left with these 9 LLMs. With 4 data sets, the company data set I talked about in the original study, but also 3 other data sets, 1 C, 1 C++, and 1 Java. And we tried them out first on those 3 publicly available data sets. And these 2 consistently performed poorly. These 3 consistently performed well, with QBERT being the best of them, the best breed. And we said, okay, company, we'd love to try those out on the 13 million lines of code to see if we've made an improvement. And they said, well, we don't really want to do the same test on the same code 3 times. We're getting no new clones out of that. And we said, well, could you do it with at least 2 on 2 of them? And they said yes. So we picked QBERT because it was the outstanding candidate. And these 2 were very similar, but we ultimately picked this one because it produced results that were very different from QBERT. These produced results that were more similar to QBERT. So we thought we'd get more of a bang for our buck there. And this is what happened. This is the example I showed you earlier on with the removed white space. We got 192 clones. QBERT gave us a few more, but CodeG5 just excelled, gave us about 2.5 times the clones we had in the, so that was a big whammy. And you can see the precision went up to 39% there.
Those are not false positives.
No, that's their true positives, yeah, exactly.
Oh,
A lady engineer went through 1,390 candidates and found these out. Yeah, and found it 3 times for 3 different models. So that was great. Because we had 9 different LLMs, and because we tried them out on 3 different data sets, we began to do analysis of what are the characteristics of the LLMs that seem to work well and not work well. And we got some surprising results. I won't go into all of these, but this one's kind of easily accessible. It turned out that, you know, when the LLM was trained on C, C++, and Java, the data sets we tried it on, that didn't help. It made things worse. And we think the problem there is the fact that it was 3 languages, that you lose the specificity for each language based on the fact that you've trained it on 3 different languages. So it loses some Java specificity, loses some C++ specificity, loses some C specificity. There were a few other surprising findings there that will make interesting research going forward. So that was the characteristics of the underpinning LLMs that seem to affect their recall. And the final research question then was, well, 1 LLM good, 2 LLMs better, maybe we could hybrid in some way. So what we did was we said, well, we could try and hybrid the models, but that's going to be extremely complicated to figure out, changing the models so that we could, in some way. So we're going to do the results instead. And there were two ways there. One was, simple heuristics. We pick the top of this one, then the next highest one is that one, then the next highest one is that one. So that's what we get in our list here, some sort of heuristic like that. Or we could use AI to combine them and see for the best possible combination they could come up with. Now, we only got this far in our research. So we looked at the heuristics. And the heuristics break into two parts. First part is normalization, where one technique comes back with scores between 0.9 and 0.7. Another technique comes back with 0.5 and 0.3. They've got to be normalized, or else the answers you're going to get are all this technique. So you've got to try and normalize those. And once you've them normalized, you've got to figure some way of aggregating them together. Do you just use the top next figure, or do you sum them, or do you average them? So we had a number of normalization strategies and a number of aggregation strategies, and we tried them all out. And the results were that ensembles don't really work on the smaller data sets, but on the in situ large data set, the 13 million versus 300 million lines of code, they do work. And the ensemble, you get a bang for your buck, probably because there's a greater diversity of clones in that larger data set. But it's very dependent on the normalization and aggregation strategy. So min-max was a good normalization strategy, and sum or max was a good aggregation strategy, resulting in about a 40% bang for our buck again, on top of the previous best results. And non-normalization on average was very bad, so you didn't get any real. You actually got a bit of a decrease if you use that aggregation strategy. I think there was a lot of applied benefits from this research. The company are now using our tool instead of their existing tool for code detection, which is great. We're struggling through our way to two invention disclosures. Conor will know about that, and in IP transferences, even though they are using the tool. We've also had several academic papers out of this collaboration, so that's really good. But I think the big bang for buck was the collaboration, the reputation gain. So here's a quote from the head of their open source competency center. Initially envisaged as a 2-year project, but was extended for 2 more years based on the success of the original project. The project was very successful, and robust prototypes have been successfully used within the company code with impressive results, and it is envisaged that they would be used going forward, and that's what's happened. And I think I've got another Huawei project based on the results of this project. Well, I have another Huawei project. I don't know whether it's on the results of this, but I think it had to help. So there's lots of interesting what next research, those surprising findings I talked about, ensembling via the meta model, via AI meta models. But I suppose what it really taught us was that, software engineering without AI is not going to be feasible going forward. It's a better way of doing anything that I've ever done in the past. And I suppose that led to a new project with AWS, which is all about teaching the next generation of software engineers in this AI for software engineering world. So that was another outcome of this project. And that's it. Thanks very much. Any questions? Yeah.
So, did you have any difficulties getting the company to run the code? Like, did they ever have a situation where you gave them code and it failed to run?
Yes, we had an initial, and they knew it. We signaled it. We said, look, we've tried this on various data sets, but we've always taken 1 or 2 missteps along the way and had to fix it for that. It was kind of awkward because they wouldn't let us see the code, but we worked through to the stage where we finally got there. Yeah.
So about the initial source projects, open source code, the original, were they sure about the originals, or they were just suspicious about?
Yeah, no, they had a criteria. They selected the open source projects based on criteria they had thought of. So they had found clones from there before, or they were in the same vertical as the company's vertical, the 13 million lines of code. So they went to an effort to define the 300 million lines of open source code we looked at.
Just one, I guess, with the increased use of things like cloud code and these, I suppose, from the generating perspective, are we going to see a lot more cases of inadvertent or unknown cloning?
A lot of those tools now come with disclaimers, they come with coverage. So they say you will not be caught for cloning, and we won't do that, and we'll cover you for it if you are caught for it. So they've taken that out of the equation for AI. But of course, you will inherit the vulnerabilities of historic code that wasn't, and hackers are always thinking of new attacks. So if you're using old data sets to create your code, you're not going to be protected from those new vulnerabilities. And so that agenda is probably bigger, not smaller.
Cool.
I even stuck within time. Sorry.
Yeah, very good. I'm impressed.
Okay, so next up is Cristiano.
Thank you very much indeed. Hello everyone, it's my turn. My name is Cristiano Storni. I work in CSIS. My presentation is going to be slightly different because my background is different. I come from design disciplines as well as social science. So while we have heard about technology and technical stuff, now we're gonna hear about people using this stuff and the consideration that people like me develop around what we need to design to help people in their daily life. And what we are looking at is chronic diseases, think of hypertension, diabetes, things that cannot be fixed, things that you need to learn how to live with. And the big questions on how to design technology that help people to take care of themselves outside of the medical attention, outside of the clinical settings. Most impactful research is now a current ongoing research. So what I'm going to present today is slightly old. It was my early days here in UL, around 2010, 2015. That's 5 years where most of the outputs went out. And why impactful? Well, because I guess a greater proportion of my citations revolve around these papers about self-care, where I would say I established myself as a visible member in the human-computer interaction community when it comes to health-related technology. And impactful because I think back in the days, part of the effort was that of changing the narrative, changing the discourse around what this technology was supposed to be doing. And I can see today, everyday technology from fitness bands to health monitoring devices, they actually seems to have incorporated some of the claim or findings or critical consideration that we brought to the table back in the days. So that was the agenda. The research was called Reassembling Health, this idea of rethinking how we think of health and the role of technology. And the background, the scenario was this: the storm is coming. We have an aging population. We have a growing population. We have skyrocketing healthcare costs, and we can't afford them anymore. And clearly, on these chronic diseases were also growing, also as an effect of aging population, the results of modern medicines keeping us alive, even if we are very sick. And so there's a lot of need. And the idea back then, and it's still kind of a recurrent hope, is that technology can fix this problem. And the idea is we're going to create a lot of technology and we move it from the clinical setting to the domestic setting, empowering people, the patient, to take care of themselves. That was the idea. We invest a lot on personal technology so that people can take care of themselves, and we will lower the centralized health costs, and we will deal with these issues, particularly the explosion of chronic diseases. So that back in the day felt like, this is something quite new, and almost historical movement of technical, of medical technology from the clinical settings where this is used to be to the domestic environment where we don't usually have this type of technology. So the question for me was, how do we design this technology? The environment changes, the context changes, the people using it changes. Do we need to design with the same assumptions that we have always designed clinical technology for clinical settings and expert medical users? And why it is historical and why it is important to look at this almost historically, because it wasn't always like that. What we take for granted in the role of medical technology as well as our relationship with the GP, it is the results of the establishment of modern medicines. But before that, it wasn't like that. Before that, we had these, the early days, we had this, which was called the bedside medicine. You have the little village and you have the doctor who actually goes to the patient house. He or she, probably a he, would sit next to the patient and establish a dialogue of probing with question, listening to the narrative and trying to capture element for a diagnosis. A sort of a more peer-to-peer Socratical dialogue, if you like. But then with the establishment of the clinic, the establishment of the modern medicines, even as a form of knowledge, obviously a sort of a strong asymmetry, separation between the doctor and the patient has been established. Now it is the patient that goes to the clinic, surrounded by people with white coats that speak a language that is not the patient language anymore. You don't have to actually tell a lot of things. Now they have diagnostics tools. You rather have to shut up rather than learn to become articulated about your own symptoms and your own body and on and on and on. And so a whole set of assumption has been established around the medical technology that sees the patient as quite passive, as quite silent, as something that needs to be fixed. And the doctor is the expert, those who knows better, those who have the diagnostic tools, those who have the knowledge, and those who gives the order to the others to be full. Now, from a sociological perspective, this obviously has been looked at critically, also looking at medical knowledge as a sort of a monopoly of expertise and a claim of obedience. You know, if I claim that there is objective knowledge that you should do that, and I'm telling you to do that, it's a demand for obedience. So there is a strong asymmetry, societally speaking. And I wanted to argue that this asymmetry is embedded, incorporated in the medical devices themselves, in the way we develop this technology. And I took the example, for instance, of the stethoscopes, a traditional piece of equipment for any general practitioner. And we let's go back to the bedside medicine for a moment. You know, the doctor, he has to learn to listen and capture things from the narratives of the patient and do a diagnosis. Now the situation, as soon as we introduce this little object in between these two people, the situation changes. The doctor is still a very good listening, but now he, probably still he listened to sounds and he learned how to capture things that are relevant for the diagnosis there. The patient should remain silent, is an object now to be investigated. And the patient also lose the opportunity to actually talk about their own subjective experience, the lived experience of their disease or whatever it is. And so, again, this assumption of the medical doctor being the superior knowledge, having superior knowledge, the patient having to comply, it is embedded, inscribed in the very same technology that we design. So now that we have this huge explosion of chronic diseases, and that technology seems to be the way to go. Back in the day, 2010, 2015, cell phones, you know, everybody had cell phones, and they were turning into medical devices, journaling, self-medication, self-diagnostic. A lot of things were being explored. being a sociologist or an anthropologist coming from qualitative studies, my way of addressing that question is I need to know more about them and what they experience. And so I joined a support group for diabetics in Ennis for 12 months. I was going there 2 hours every second Saturday, picking up what they were talking about, their problems, their perspective, how they fix things, how they advise one another. And what I have learned is that the lived experience is very different from what I was hearing from the endocrinologist, who knew a lot about diabetes, but he has never really experiencing it. And so I started to interview these people and started to learn about their experience, and obviously very impactful thing, having diabetes. I mean type 1, insulin-dependent diabetes, with others having to self-inject insulin quite a few times a day. And it changed the way you see the world, it changed the way you are in the world. And what I also found that these typical traditional asymmetry between the doctors and the patient, which is okay in acute disease. I mean, if you have pneumonia or if you are in a car accident, just shut up and do what you need to be doing. But if you have diabetes and you live with it 24/7, it's not just about compliance. You know, you are a father, you are a worker, you love holidays, you might indulge into a party, and all these things highly affect or are highly affected by your diabetes. So, and then this asymmetry was problematic for them. They say, well, you know, it's hard to find a specialist who acknowledges that the patient knows just as much. You know, the assumption felt by the patient is, oh, I am the doctor, you're the stupid patient, you do what I tell you. And I felt bad about this because these people need to collaborate. And they were actually in conflict. And say on paper is not hard, because the endocrinologists, they look at the journals where the diabetics have jotted down their numbers and they make judgment based on those journals. And they say, well, on journal it's not hard, but in everyday life it's just very, very complicated. And they were blaming each other. I said, well, this is not really something we need. And again, this sort of a reductionistic medical gaze. He only looked at numbers. I'm just more than just numbers. And this one was very interesting. I had this one diabetics, and you know, diabetics, they are, especially in the early years of self-managing, they journal their glucose levels. It's a common practice, but what they're given typically by the medical staff is these pre-formatted journals where they only have space to introduce the insulin and the dosage of the glucose readings and the insulin that they self-inject. Just a couple of numbers. But what she had is, I typed those extra information out of my doctors. She had 2 different journals. One was for the doctors, reflecting a medical perspective on what diabetes is. I give him the numbers, he wants the numbers. But then for what I care, I have this much more complex, articulated, rich diary packed with vouchers and pictures and cuts off and little graphs, some maths on the corner, and notes, a recipe. It was very, very much more different and articulated and unstructured. And I said, well, this is a much more authentic reflection of what diabetes is from the perspective of those living it. If I have to design a journaling system, I have to have this model in mind, not the doctor model in mind. And so I started to say, hey, but when we design technology, we have the acute disease model approach in mind. We have this metaphor of control. We live in a domain of certainties. Care is episodic. Compliance is a good metrics there. But if we look at these new emerging models, all those little things, they start to, in chronic disease, what worked today, it doesn't work tomorrow. We are in a constant domain of uncertainties. Care is continuous. The asymmetry between the doctors and the patient is not really there. The patient, they develop what I eventually end up calling a lay expertise, forms of knowledge that are not medical, but they're actually helping them to tweak and adjust and live with the disease, going beyond just compliance. So the question was, and then of course a lot of literature that was somehow reaffirming that creating technologies that gives numbers, for instance, it would draw the attention to those numbers and we will forget about things that are difficult to count. And also almost assuming that things that are difficult to count, they might not count at all. Which in a domain of uncertainty is really a problem. This is also called as the McNamara fallacy. I don't have time to go through this, but you have the slides. And this is a very, very important critical reflection on reducing everything to numbers. And so obviously the idea was, and I'm almost done, to rethink the way we develop self-monitoring technology in chronic disease, going beyond just pathologizing, medicalized definition of what that chronic disease is, but looking at the lived experience and seeing how a messier picture. And what we came up with was a journaling system that would allow people to actually create tags. Back in the day, we called tags lay categories of data, which the patient themselves consider to be very relevant for their own care practices. The idea for me was, well, that 17 years old that I have interviewed, he was complaining about not being trained on how to get drunk when he's diabetic, when he has diabetes. And the doctors, the endocrinologist, is not going to give him tips on that, right? And yet that guy is going to get drunk, right? And he's going to get drunk unsafely because there's nothing that helps him or her to actually tweak, learn. So I wanted to design a technology that ideally could help a 17 years old to actually learn how to get drunk without getting into a coma. And you do it with little experiments, and the only way to do it is that you are allowed to actually jot down things that the doctor doesn't want to hear, like alcohol intake. I give you another provocation. People might find benefit in praying. And a scientist will say, oh, how can you say that? Well, meditation, there's a lot of things. Can we allow people to monitor that thing and find some evidence that that actually works for them? Maybe it works for other people too. So that was a moment where I started to see patient as potential subject contributing to new knowledge generation, that it doesn't necessarily have to come down from the trickle-down model of big medicine and big corporations. Why don't we have like a lot of people monitoring their own shite and then coming up with perhaps hypotheses on what works and what doesn't. Why this was impactful? Because today's technology, they leave a lot of room for people to add notes, to add extra categories of data. I have this aura, and he asking me, hey, last night you didn't sleep very the same. Did you eat too much in the evening? Or there was something else that we don't know you want to add? Other people in the same situation had this, and that. Maybe you did it. So they're doing research in a bottom-up fashion as well, which I think, well, they have read those papers back in the days, because back in the days, we couldn't, only medical information, and everything that was somehow going outside that was considered fraud in a way. Thank you very much.
So I could ask the first question. If
Oh,
that's
yes,
as basic as I can.
please.
So did you do anything after that? So you proposed it. Did you create an app? Did they use it? Did you do bottom up?
We actually, yes, we tested these. Well, we tested in a very modest way. We had 4 iPhones and we gave 4 people for a month, and then we asked them to keep a diary about how they felt. It was great because they could actually visualize things and say, well, if I play a fave aside, I'm learning now. I need a couple of less unit of insulin because I'm gonna burn sugar.
Yeah.
Now I exactly know what it's to. Before I didn't know, but now after a couple of times marking it, thanks to this, and no other journaling system would enable me to do that because I can't add my soccer in it. I can learn how to make it work. People learning that if they run on a sunny day, they need less insulin because they sweat more.
Yeah.
You know, little things that are very idiosyncratic, but they make a difference in terms of everyday life, self-caring, and having this sense of control and empowerment, which if you reduce everything down to those 2 numbers, you never get. That was the idea, and I think it worked.
Great. And any other
Thanks.
questions?
Do you think people who do research are affected by their own experience? In other words, if somebody's got an autistic child and they're doing research into autism,
Well, when you have
No,
your
I mean-
skin in the game, obviously,
well, people who are affected are the researchers. That's what I'm saying. So, you know, they have a different perspective.
fair enough, I guess. Are you asking if I was diabetics, would I have done this research differently?
Well, here, to me, the people who are affected have control over the research,
Yes.
which is, you know, it's,
Oh, they run
what I
research.
mean?
Yeah. Well,
Yeah.
I'm not sure if I'm getting you, but yes, this could be seen not just a journaling system to report things to the doctor, which is what the traditional journaling system is about. This is a research tool.
yes.
I can have questions about something and I can start, at least I'm supported to monitoring it a bit more systematically, and I have some facilities to try to visualize it
Yes, rather than sort of
rather than trying to do it myself.
yeah, rather than to do an analysis. Oh, I have a peak here. They let it completely open to the patient. You would
Yeah,
say.
yeah.
They say, oh, I have a why is that? I have no idea why that happened. You know.
So see again, then a lot of knowledge comes from comparing. So a lot of we wanted to give the ability to compare little things, compare that moment, compare with that, compare with that. Obviously, it's in the wild. It's not a controlled environment. It never works the same. But they also have, interestingly enough, validation practices like scientists. For instance, they have the rule of 3. Something that works twice is not good enough. It has to work 3 times in a row. Then I've learned something. These are heuristic, if you like, but nobody studied them in a way, you know? Thank you.
I think we've got to wind it up now, but that was really interesting.
Cheers.
Thanks.
Thank
Ian.
you very
Yeah.
much. Thank you.
So I think that's the end.